Well, welcome. Today is Thursday, November the 12th. This is AP Chemistry at Spain Park High School. And if you are enjoying these exciting videos, learning AP Chemistry each and every day, please feel free to subscribe to my channel. All right. Today we're going to just go over these. But anybody that's on a scale of 1 to 5 with an AP test, a 5 meaning you did really well on these. Would anybody think you got a 5 if I was to grade these 4 or 5 questions on an AP scale? No? Oh, there's my email. So, let's look at number 5. Number 5. So it says, draw the Lewis structure for PF3 and PF5. Okay? So if I want to go and I want to draw that Lewis dot structure, PF3, what do I do? Count the valence electrons. 5 plus 21 makes 26 electrons. Okay? Essential atoms: phosphorus, fluorine, fluorine, fluorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. It's all good. All right? Then PF5, what's the only thing going to be different? The shape, but you're going to go, you have 5 around it. Now if you want to, basically you're going to split this lone pair and each one's going to bond. Is what really happens. But we have with PF5, you're going to end up with 7 times 35, 40 electrons. 2, 4, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Now you must put the lone pair, as big of a pain as it is. You have to put the lone pair on there. Now, is PF3 polar or is it non-polar? How do we know whose mother is polar?
Me?
Yeah.
It has a polar bond because of fluorine. Like it's
Okay,
different.
so it's got a polar bond because it's with fluorine, and
it's asymmetrical.
Well, asymmetrical what shape?
T-shape. Oh wait, no. Trigonal.
Trigonal pyramidal. Okay? So it contains a polar bond and it's asymmetrical. Now this is the wording that you need to really learn how to put into this. This is going to come in almost all of them on 7, 8, 9. Okay? The asymmetrical shape, asymmetrical trigonal pyramidal shape results in what? What did I say? An uneven distribution of electrons, causing it to be polar. You need to get in there. The asymmetrical trigonal pyramidal shape causes it to be, causes an uneven distribution of electrons, causing it, making it polar. Okay? It's very important on polar molecules you say an uneven distribution of electrons. Now, on the basis of bonding principles, predict whether each of the following would exist. Okay? Now, where are nitrogen and arsenic in relationship to phosphorus? Above the same family, right? So they should all bond the same way. Why can't NF5 exist? Or does it exist?
Make it expanded octet.
Okay? Because it is too small. Okay? In order to form NF5, it would require an expanded octet. The nitrogen is too small to be able to accommodate more than 8 electrons. Whereas ASF5, arsenic, is a much larger atom. It does exist because it's large enough to form an expanded octet. Okay, one's too small and one's big enough. All right? Now, remember this PF3 and PF5 one. Because now when we go to number 7E, well, this one doesn't relate to that. But look at D. Phosphorus forms, this is just a different year. It doesn't say what year, but it's just a different year. Phosphorus forms PF3, PF5, whereas nitrogen forms only NF3. Exact same question as we just answered. Okay? So there's only certain ways they can ask a question, you know, and so they can just change the elements in the period. They could have said ASF3 and ASF5 form, but NF5 doesn't. Anything in the family. All right, so this is a flashback question. This is just kind of a review from last unit. A water solution of iodine is shaken with an equal volume of non-polar solvents such as trichloroethane. That would be a chlorofluorocarbon. Describe the appearance of this system after shaking. Okay? Iodine is polar or non-polar?
Non-polar.
Non-polar. So is it going to be more attracted to the polar water or the non-polar TTE?
Non-polar.
Non-polar TTE. What do we know about the water and the non-polar TTE? Will they mix?
Yes. No.
No. It's just like oil and vinegar. The vinegar and oil mix in a tiny salad dressing. They quickly separate. They form an unstable emulsion. An emulsion is a mixture of two things that are forced to be together that don't really want to mix. Okay? So the iodine, when it's in water, barely dissolves, and if it does, it's going to be a slight yellow solution. But when it completely dissolves, it's purple. So I put it into water, but then you're just going to pour this in here. You're going to get two layers to separate, and the iodine will be purple in the TTE, which will probably be sitting on top. Most of the time the oils sit on top. They're less dense than the water.
But I thought they were both non-polar.
Water's not non-polar.
But TTE is.
I know. So like dissolves like. Polar dissolves polar, non-polar dissolves non-polar.
Yeah.
So the iodine is really, when they talk about iodine in water, it's a very low concentration of dissolved iodine.
Oh.
Now, I don't know if you've ever heard in pollution, one type of pollution they call TOCs, which are total organic compounds. What's the total organic compounds that are dissolved like in a river or a lake or whatever that's in there? Well, when they take that out, in order to get a amount that's measurable, they have to concentrate it up. So they take the water, and the organic compounds are going to be non-polar, so they put a non-polar solvent mixed with it, and that extracts out the organic compounds, the non-polar compounds from the water, because they're going to be much more attracted.
Students are going to 7th period at this time.
Okay? So, we just started here, so let's just finish this. I'll give you a break in a little bit. Okay? I don't want to stop there. So the iodine is going to go much more go in with the non-polar TTE, so you'll have a layer of TTE with iodine dissolved in it, and then a layer of water.
It says after shaking.
Yeah, because you're going to shake it and then it's going to separate.
You don't talk about immediately after it's shaken?
No, it's really going to be, you have to shake it. The shaking is going to allow the iodine and this to combine.
But
If you
when
just
like
didn't
us,
shake
just
it,
like
if you didn't shake it, then the two layers are going to separate and the iodine will never have a chance to get with this.
Mackenzie Culpepper,
They'll
come to the front
separate
desk,
very
please.
quickly.
Mackenzie Culpepper.
Are we supposed to wrap all the time purple?
No, but I mean, I actually should, when we start working on the next round, I'll go get the stuff and I'll kind of show you what this actually is all about. I'll do it. Okay? All right, so that was 7. Number 8, great question, number 8. All these are great questions, I like them all. Howdy. So, I'm going to call on some of y'all to answer these. Solid K conducts an electric current, whereas solid KNO3 does not. Carrie, what'd you get on that?
solid K is metallically bonded, so there's a sea of electrons where electricity can flow through. And solid K-3 is ionic, so it's in its crystal structure or electric current.
Okay, because of the crystal structure, what does that mean about the ions?
You can't.
They can't flow.
Okay, the ions are held rigidly in place and cannot flow. That's the only thing I would add to that. Okay? She mentioned potassium is a metal. Sea of free-floating electrons allow the flow of current. KNO3 is ionic solid. Okay? Ions are held rigidly in place in the solid and therefore cannot move and conduct the electricity. All right, Angel. SbCl3 has a measurable dipole moment. What does it mean to have a measurable dipole moment? It's a measurement of a molecule's polarity, right? So this is foreign language to us. We have to interpret this. SbCl3 has a measurable dipole moment. What's another way of saying that? It's polar. And the SbCl5 is not. Now, again, Sb, same family. We've already talked about phosphorus and arsenic. Antimony's in the same family. This was really the same question, just dealing with polarity, because it asked whether or not the PO3 was polar. Okay? So this is polar. Why?
Asymmetrical.
Hey, okay, but Angel's answering this one.
Asymmetrical.
Okay, so what does that cause?
The uneven distribution of electrons.
Okay, the asymmetrical trigonal pyramidal shape results in an uneven distribution of electrons, causing it to be polar. Whereas, you always have to mention both. SbCl5 is symmetrical, what shape? Trigonal bipyramidal shape, which results in what type of distribution of electrons? An even distribution of electrons, making it nonpolar. I'm going to be super specific, picky, that you use those words. When we're dealing with polar and nonpolar, even and uneven distribution of electrons. I should say that the other way. Polar is uneven, nonpolar is an even distribution of electrons. Due to the asymmetrical trigonal pyramidal shape, due to the symmetrical trigonal bipyramidal shape. Now, what's the second criteria for something to be polar? Polar bonds. So I would start this by saying both SbCl3 and SbCl5 have polar bonds. However, the asymmetrical trigonal pyramidal shape of SbCl3 results in an uneven distribution of electrons, causing it to be polar, whereas SbCl5 has a symmetrical trigonal bipyramidal shape, causing it to have an even distribution of electrons, making it nonpolar. Okay? Again, but they're asking the same question year after year after year. The normal boiling point of CCl4 is this, and CBr4 is that. Zane, what do you got?
Bromine has a larger electron cloud than chlorine. Therefore, the electron cloud in carbon tetrabromide is more polarizable than the electron cloud of carbon tetrachloride.
Okay, it's more polarizable, but what does that result in?
So,
Oh, you're not finished yet? Oh, you weren't finished. I thought you were finished. Go ahead.
we're only halfway.
Okay, keep going.
So the CBr4 London dispersion forces are greater than the CCl4 London dispersion forces. Greater intermolecular forces leads to more energy being needed to boil a liquid, and thus the boiling point of CBr4 is higher than that of CCl4.
Okay, that's a very good answer. Okay, it's a little overkill, but it's a very good answer. Okay, and you're never going to get wrong because nothing you said was incorrect. So that's a very good answer. What's the key? Both substances are what? Non-polar, covalent molecular, right?
Yeah.
So the first thing we do, is it ionic, is it metallic, is it covalent network, is it covalent molecular? It's covalent molecular, okay? Then when you're dealing with boiling points, then you have to deal with attractive forces. So then you have to go, okay, covalent molecular, is it polar, is it non-polar? How do we know that these are non-polar?
It's symmetrical.
Okay, AX4, right? All same bonding atoms, it's a symmetrical molecule, both of them. So therefore it's nonpolar, so what's the only type of attractive force or intermolecular force? London dispersion. And notice that Zane put in his answer that the CBr4 to CBr4 bond, he stressed it's an intermolecular force. You don't want to say that the carbon to bromine bond is, because that's not what's going to break, the carbon to bromine. You don't want to say anything about that bond. You could say the intermolecular forces between CBr4 molecules are going to be stronger than the LDFs between CCl4. Between molecules is really important on that. So you don't imply that you're breaking the carbon to bromine bond versus the carbon to chlorine bond. It has nothing to do with that because we're breaking molecule for molecule. Whew. This one's a good one. This is a flashback question too. NaI is very soluble in water, whereas I2 is a solubility of only 0.03 grams per 100 grams. Okay? Who wants to answer this one? Anyone going to volunteer? Okay, just when you looked at them, you're the only one looking. Everybody else was looking down.
Sodium iodide is an ionic compound, and when it's placed in polar H2O, it can be pulled into solution.
Due to strong, what do we call the forces between polar water and an ionic compound? Not dipole.
Ion
Dipole.
dipole.
Ion to dipole attractions. Okay, I would make sure that that's in there. Strong ion, because whenever two things are soluble, that means you got a strong solute to solvent attraction. So the strong ion to dipole attraction is allowed to be soluble, whereas, keep going now.
I2 can't dissociate because it's covalent, molecular, nonpolar, so it can't be put into solution.
Because, what's the type of attractive force between a nonpolar molecule and water? Dipole-induced dipole, which are too weak to overcome
The dipole in H2O.
the dipole-dipole or the hydrogen bonds in H2O, causing it to have limited solubility. Okay? Ion to dipole, dipole-induced dipole. Ion to dipole is a strong attraction, so it's soluble. Dipole-induced dipole is a weak attraction, too weak to overcome the hydrogen bonds in water, therefore it's very insoluble. Or only slightly soluble. Okay? That was last chapter really. Yes, sir.
Could you say, because it's an ionic compound, water's it's able to hydrogen bond to the ions, thus overcoming the lattice difficulty?
Well, but that one, these aren't forming hydrogen bonds with water.
I thought water hydrogen bonds to the.
Hydrogen bond. A hydrogen bond is going to be an OH on one to an oxygen on the other. You have to have the hydrogen trapped between either an oxygen, nitrogen, or fluorine. Okay, so it's only those atoms that are going to form hydrogen bond with each other. It's the energy of hydration, we talked about that, but it's not a hydrogen bond. Ion to dipole attraction. All right, number 9. Threw a curveball at you on number 9.
Nice.
Some of y'all asked me about it, or maybe you kept talking, but you have NO2. This is the brown gas that we did with our pen, that came off from our pen. Nitrogen dioxide. We count electrons. 5 plus 6 times 2 is 12. We end up with 17 electrons. Whenever you have an odd number of electrons, we have a unique situation. Let's draw the Lewis structure the same way. Oxygen, oxygen. 2, 4, 6, 8, 10, 12, 14, 16. Extra electrons always go, so we only have one though. This is what we call a free radical. Contains an unpaired, a compound that contains an unpaired electron. Very reactive, okay? If any of y'all watch any kind or read anything nutritional, you'll read about foods that are antioxidants. to help tie up and eliminate the free radicals inside of our body. Okay? What would an antioxidant, what would we call that? What's the other name of an antioxidant? Okay? Do what?
Reducer.
A reducer. An antioxidant, something that oxidizes, the antioxidation is a reducer. Okay? I don't know why they call them oxidants, rather than call them reducing agents or whatever, but it's going to reduce it. In other words, it's going to add electrons to this to make it more stable. Yes, ma'am.
So, when I did it, I put it as 1 O had a double.
Well, we're not done yet.
Oh, okay.
Okay? Because nitrogen only has 2, 4, 5. So we can at least make a double bond. Now, a lot of people wanted to go and put a double bond there as well. But how many electrons would that put around nitrogen? 9. Can nitrogen have over 8? No. So 7 is where it's got to end. Okay? Now, when we do the AX formula on this, it's still AX2E. Because that electron is still occupying this third orbital. Okay? But there's only one of them there. We'll see how that in the next part of the question where that's going to come out. Okay? Now, I could have put the double bond there, right? Therefore, Uzma, what property does
Resonance.
That's right. Okay, so we have potential for resonance. So what would be my bond order here between the nitrogen and the oxygens?
1.5.
Both of them would be 1.5. So both bonds would be identical. 1.5 bond order. Okay? Now we go to NO2 minus. What's the minus mean? One more electron. So we have 18 electrons. So that just means we're going to be able to do that. Okay? Put it into brackets. Mr. Sluss, most of them on the quiz did not put brackets even though you had stressed it. Okay, I said most did. I said it's not all did. Okay? Well, there were several people that way more than one that did not. So, what's the AX formula here? AX2E, okay? So the shape here is going to be bent. The shape of this one is going to be bent. And then finally we get NO2 plus, which means we're going to be 16. And in order to make that work, we have to do it like this. Now, is there resonance potential here? No, there's only one way, 2 double bonds, right? So what's the AX formula here? AX2, so what shape does that make it? Linear. So, list the species in order of increasing bond angle. Well, let's start here. What would the bond angle be on this one?
180.
180. All right? But what's the bond angle here? Even on this one, what do you think?
107.5.
No. This is AX2E, so the shape is starting at
120.
trigonal planar 120. The lone pair occupy a greater space.
Like 110.
They're not that far. It's like 1 to 2 degrees. Okay, about 118, 119. But if there's only one electron up here, are we going to have electron-electron repulsions? No, so it's not going to swell and take up more space because we don't have that electron-electron repulsion. So this one's going to be 120. Okay, because it's AX2E, it's got the 3 electron pair domains. It's going to be, the electrons are going to be in the 120 trigonal planar arrangement. So if we want to increasing, it's going to be this one, then this one, then this one. Okay? Middle, left, right.
What would it be, 120 exactly?
Probably pretty close.
But wouldn't there be some effect from that single electron on the other two?
No, okay, they're all repelling each other, but they're going to be repelling equally.
Yeah. So it does still push them, right?
Yeah, it's still pushing them down, that's why we're at 120 and not 180. So without the electron pairs up here, then it goes totally straight. So that electron is definitely still occupying a space, still definitely negative, still affecting the shape, causing it to be bent. But it's not going to cause the bond angle to decrease it because we don't have the extra electron-electron repulsion. Select one of the species. What's the type of hybridization on this nitrogen? sp2, right? sp2, sp. Is everybody comfortable with determining, that's all you have to know for hybridization. Is everybody comfortable being able to do that? Remember, the AX formula is never part of the answer. It's just a way to get to the answer. It's an easier way for us to kind of just have a general trend. But whenever it asks for hybridization, shapes, you know, all that, the AX is never going to be part of the answer. So, you know, don't say type of hybridization, it's AX2E. That's not a hybridization. And then, here's another crazy thing. Identify the only one of the species that dimerizes. Hampton, what would a dimer be? Any idea?
No idea.
Does anybody know what a polymer is?
More than one monomer.
More than one monomer, what do they do?
Together?
Link them together, right? So a polymer has many monomers just all stuck together in this big old long chain, sometimes 100,000 carbons long.
Wow.
Okay? So what would a dimer be?
2 monomers.
10 of them.
10?
9? 10? I don't know.
Remember we have carbon dioxide,
Oh, 2.
means 2. Okay? In other words, which one of these would have 2 coming together? Sugar is a dimer. You have the monosaccharides, they're the starting material. I think sugar is a glucose and a fructose, not 2 glucoses, or glucose. I think it's a glucose and a fructose coming together to make the disaccharide, the more complicated sugar molecule. Okay? Which one of these is going to want to bond and make a dimer? Why? Why this one?
That's the single electron.
Because it wants that single electron can bond with another one, so we can end up having this nitrogen like this, and then we have the double bond oxygen here, double bond oxygen here. We'd have resonance kind of on both of these as it sticks together with this bond right there. All right. Did anybody get that on their own? Kinda? That one, I know that this one, it gets that one every year, the dimerizes, but we've never seen anything like that. I like you to kind of think through those. Finally.
You searched it up, does that count?
Do I?
You searched it up, does that count? What dimerizing?
No, I didn't have to.
I just got it.
I took-
Because it's in the middle. Oh,
All right. Experimental data provide the basis for interpreting differences in properties of substances. Account for the differences in properties. So we look at magnesium chloride and silicon tetrachloride. Okay? Zoe, did you get an answer for this? MgCl2 is what type of compound? Whereas SiCl4 is what type of covalent?
Molecular.
It is molecular, but polar or nonpolar? Nonpolar, because it's symmetrical. Okay? So when you melt, we're talking about melting points. When you melt MgCl2, what are we overcoming? Is it intermolecular for ionic?
No.
It's Coulombic attraction, right?
Yeah.
What do we call the energy needed to break that attraction? The lattice energy. Okay? So MgCl2 is an ionic compound with high lattice energy, requiring lots of energy to break the ions apart. Whereas SiCl4, being a non-polar molecule, what does it have to overcome to melt? Between the SiCl4 molecules, right? MgCl2, the Mg and the Cl actually separate from one another. You're breaking the ionic bond. But when a covalent substance melts, you're breaking molecule for molecule that only has the weak LDFs holding it together. It takes way less energy to break it apart. Yes, sir.
Is there like an equivalent for covalent substances where you break apart the covalent bond?
I mean, we call it bond energy, where you decompose it. When we get into thermo, we'll talk about that. But generally speaking, under normal circumstances, that's not going to happen. But when chemicals react, the bonds do break and other bonds form, and so the difference in those energies is what, you know, it's either endothermic or exothermic. So we'll get into that, but it would be the bond energy. But that doesn't occur in melting for covalent substances. All right, B, MgCl2 and MgF2. Grayson just refuses to look at me. Jaden, what'd you get for that one? Oh, the one you don't know? Well, answer C then, fluorine and bromine. The bond length. Okay, which one's got a bigger electron cloud? Bromine. It's really just bromine's bigger than fluorine, so when they bond, it's going to be a bigger bond. And like Jaden said, it's an electron cloud. Who wants to answer B? Go ahead.
Well, you have to look at the ionic radius, and for MgF2, it's stronger because the size of fluorine is smaller than the size of chlorine. They can form stronger attractions, which will increase the
Stronger what type of attraction?
Coulombic,
Coulombic attraction.
which will increase the melting point for that if you compare it to
Okay.
MgCl2.
All right? So, both substances are what type?
Ionic.
They're both ionic, okay? Which are, the ions are held together by Coulombic attractions. What do we know about the product of the charges?
They're the same.
The product of the charges are the same, but according to Coulomb's law, with fluorine being smaller than chlorine, it's going to have a greater Coulombic attraction, thus take more energy to break it apart, higher melting point. You must, on this one, both ionic, held by Coulombic attractions or electrostatic attractions, okay? Held together by strong ionic bonds, okay? The strength of that is measured by Coulomb's law. Both have the same product of the charges, but because fluorine is smaller than chlorine, the Coulombic attraction is greater, and it has a higher melting point. So there's a lot in that. But it's all Coulomb's law, really. Every question is going to have pretty much one concept that you're trying to answer for everyone. This one is Coulomb's law. This one is the difference between ionic and covalent, breaking an ionic bond versus an IMF. So this one here is about, Coulomb's law with ionic compounds. This one is about just the size and bond length. Now, F2 and N2. Notice the N2 bond length is way smaller. They're about the same size. They're pretty close to each other on the periodic table in the same period. Why is nitrogen so much shorter? Nitrogen has a triple bond versus fluorine is single bond. I don't know if we said this specifically, but the higher the bond order, the shorter the bond length. The more that you have in common, the more that you share, the closer you're going to be. Okay? Yes, ma'am.
Wait, so how do you know that nitrogen has a triple bond and
Oh, good question. Because this is just going to be something that is intrinsic, and you're going to know that the halogens all form single bonds with each other. Fluorine, chlorine, bromine, iodine, they're going to be single bonded. How is oxygen bonded to itself in the air that we're breathing?
double?
A double bond. And the nitrogen in the air that we're breathing is a triple bond. Okay? Is a triple bond. Now, if you wanted to, if you didn't know, you were confused, you say nitrogen bonded to nitrogen. They both have 5, so it's 10 electrons total. 2, 4, 6, 8, 10. This nitrogen is way electron efficient. So I'm going to do it like that. So we can share there, Share there, gives you double, triple bond. But that is something that should just be intrinsic. My sophomores were going kind of a little crazy yesterday or Tuesday, because Mr. Sandlin was singing in class. Those of you that may have had him in the past know that he likes to sing. And he actually came down the hall this morning, and so I said, hey, you're gonna come do an encore presentation for us? And he goes, no, but he goes, sometimes, when I have the super important points, we drive them home. He goes, we gotta get, you guys understand it to the skin deep, but we gotta get down into the bones. We gotta get down to where it's part of you, And that's what it is with the oxygen and the nitrogen, double bond, zinc, triple bond. That just needs to be in your bones. You just gotta know some of that basic stuff. That's how we know. I'm not gonna sing a song.
You should. Freestyle, come on.
Yeah, no, there's a reason I'm a chemistry teacher.
Please don't have to.
All right. Any questions on these first go around? We're good? All right. Round 2.
5-minute break?
Oh yeah, 5-minute break, then round 2.
When they get breaks?